Good afternoon, everybody. My name is Dougal Ballantyne. Thank you very much for coming to this session. Hope everyone had a good lunch, everyone suitably fed. We're going to be talking about performance benchmarking on AWS. I'm an HPC solutions architect. It's high performance computing, so I spend a lot of time doing benchmarking. A lot of the content I'm going to be talking about today comes from our benchmarking team, who we work closely with. I'm also going to bring up a customer as we go through our slides today from Just Eat called Benny. And he's going to talk a little bit more about how they actually do benchmarking in practice. So let's get started. The best benchmark for you is your application. Now, I know you've heard that plenty of times. We like to talk about it a lot. We have quotes about it on our website. But it truly is the best benchmark. There's often times, though, you cannot do your entire application stack on top of us. And so what I'm going to spend time today talking about is when you can use synthetic benchmarks to identify components in your application and then use those benchmarks to give you an indication of how you think your application may perform. But at the end of the day, the best benchmark is still going to be your application. When you're running these benchmarks, and the ones we pull out today are just examples, it's really important to understand whether they're giving you absolute results or relative results. So an absolute result would be the amount of work that can get done. A relative result would be, is it doing more work than the other system? I'm testing different instance types, and how much performance are they delivering? Is the benchmark a fixed time benchmark or a fixed work benchmark? A lot of the benchmarks are fixed time, meaning the more work they do in that time, the better. Other benchmarks that we're going to look at, they're fixed work, meaning the quicker the benchmark runs, the better the benchmark is. And you have to be very careful when you're using these benchmarks that you understand what that means. Sometimes they're going to run really quick, and that might actually mean it's not running correctly, and it's not that it was actually faster. And I've seen people who come away with some awesome results and realize it wasn't running correctly. What's different about benchmarking on top of AWS or benchmarking on top of a cloud infrastructure than benchmarking on-premise? The first thing is you have an awful lot of variety. There's many, many instance types, many, many configurations you can choose and use, so you need to make sure you're focusing in on ones that are relevant to your area of focus for your application. Now, we've tried to make it easier by having things called instance families, and we group them into general purpose and compute optimized and storage optimized. We do hope that you have a little bit of an idea before you start as to whether you think you're going to be needing something that's very heavy on storage versus something that's very heavy on CPU or maybe a memory optimized platform. The other thing that's different about AWS or top of the cloud is there's going to be some more levels of abstraction than, say, an on-premise bare metal system. So you want to take that into consideration with your benchmarks and run a little bit more. You probably want to be looking at running sort of 10 iterations of a test over a couple of different instances and make sure any variability that may occur is being incorporated in your testing results, and you can use that to make your decisions as to what you're going to use. Use a good AMI. Now, what is a good AMI? For me, a good AMI is one that I understand where it came from, that it's current, it's up to date, and is going to deliver expected performance. I see a lot of customers testing applications, and they have a standard, I must use this AMI, and not realizing that that AMI doesn't actually have the latest up-to-date kernels or the latest up-to-date libraries in it, and so it's not able to take advantage of the AWS platform. The AWS platform is constantly innovating. We're always launching new instance types, which means we're also leveraging the latest hardware. If you're running an AMI that didn't, or if you're running an instance type that didn't exist, or the CPU didn't exist when the AMI was released or the software was built, it's unlikely you're actually leveraging all of the capabilities in that platform. So an AMI is a really important selection. To highlight it a little bit, we took some benchmarks in the benchmarking team and we ran them, same binaries, same operating system, but different flavors of an AMI that were released out into the AWS world. And you can see that the CentOS 4 results are really variable. They're all over the place. The difference was newer versus older kernels within the CentOS 5.4 release. So if you start out with the release that came just at 5.4, there was problems in there with multi-threaded performance. Whereas if you did a yum upgrade and came to the latest kernel in 5.4, you actually got those things fixed. And so you might think that you're running on the latest. You really want to make sure you've pulled those in. So what I'm going to do now for the next set of sections is I'm going to walk you through some scenarios, some tools you could use for doing benchmarking when you can't use your application. So hypothetically, we have a CPU-based problem that we need to solve. We're looking for what would be the best instance, what instance would give me the best CPU performance. It's going to be an integer-based problem. Now, at this point, I've already made some pretty big assumptions that you've been able to identify that it is an integer-based problem that you're trying to solve. And I think it's important you do realize that, you know, when you run these benchmarks, and we're going to talk about geekbench and UnixBench and Sysbench, that, you know, they often just output a number. And that number, even if it, you know, a higher number is better in one, a lower number is better in the other, that may not mean your application is going to run better. So you should try and spend a little bit of time understanding which part of the instance or which part of the infrastructure being provided is important to your application. And so this one we have been able to determine its integer performance. So we're going to take a look at choosing a benchmark. Now, these are some example benchmarks. I'm not endorsing any benchmark per se. These are ones we run often. We see a lot of customers running these benchmarks. Some of them are open source, some of them are commercial. They all give very different results and very different approaches to testing. What I'm going to do is walk you through very quickly how we use them and how we gather the results. For those making notes furiously, all of the slides will be available afterwards. We will have a YouTube video of this talk, and I will be available for Q&A after the talk outside, and I will happily give out business cards to people if they want to get more access to what we're doing with benchmarking. So when you're running these benchmarks, it's important to understand whether you have or not a good result. And I mentioned it earlier that when you run a test and it outputs the runtime of 5 seconds, and then you run it again, it outputs 3 seconds and then 2 seconds on different instances, you need to make sure that's because the instance is actually faster and not because the benchmark didn't notice it was testing something. Maybe it skipped over a test in one of the runs. So you really want to pay attention to make sure you are getting a good result from the system. When we run our tests internally, and then the advice we give to our customers, you want to run them on a multitude of instance types multiple times. You want to understand exactly the coefficient of variance, and I'll dig into what that means a little bit, so you can understand whether variability in the platform is going to be present for your particular application. All of the tests we ran for this talk were on an Ubuntu 13.04 AMI, and we ran each test a minimum of 4 times. Sometimes we ran them more, but a minimum of 4 times, and we ran them over 9 instances, and 10 instances of those 9 instance types. So we'll dive into an actual test. So Geekbench, it's a free download in 32-bit, a commercial product in 64-bit. It's a black box. There's no source code. You just have to run it, and it outputs a number. It runs a single and a multi-CPU benchmark, so you can test 1 core or as many cores available in the system. It's really easy to set up, and it has a really fast runtime. It's broken into 13 integer tests, and these integer tests are actually collected up from different tests around, you know, the internet and pooled together. 10 floating point tests, again, tests that you can look up and determine, you know, where they come from. And 4 memory tests, predominantly based on the stream benchmark. Now, there's no source code to it, so you have no idea how they've constructed this test. You do not know any of the parameters. You don't know if it's optimized for the latest generation CPUs. You don't know how it's actually been set up. So one word of caution, just make sure you do have an understanding of whether the benchmarks are giving you the numbers you're looking for. It might be that Geekbench doesn't recognize the CPU you're on and doesn't leverage those features. So the Geekbench script, I'm going to share with you example scripts. These are going to be available afterwards, so don't worry about trying to write them down, but I'm trying to give you some thoughts and methodology around how we do our benchmarking or how we collect benchmarking. We want to annotate all of our results to let us know what instance they ran on, what time of day, what the test was, and how many iterations we ran. And it's nothing complex. We're not writing a really fancy testing framework here. We're just leveraging some bash scripts, but it means that all of our results are going to be easily parsable. To run Geekbench, it's very simple. You run Geekbench, specify no upload, so it doesn't upload the results to the Geekbench website. And then I've got some timing around it, a start and an end, which is pretty simple and naive. And then I'm able to work out how quick the benchmark ran, so from start to finish, and then an output name, and I copy that out. You also want to upload these, as I personally upload anyway, to S3. You want to store these results everywhere. Keep all of your test results. Every time you run a test, please save those results somewhere. S3 is typically the easiest place to do that. You can come back to these 6 months later, 6 years later, and see whether things are still consistent, whether they've changed. It's important to do that. So let's take a little bit of a look at the results that we got when we're running the geekbench on AWS. What I've done with these results is I've put them together in a baseline format. So I'm actually going to take one system, use that as my baseline, and that's going to be the CC2 8 extra large. And it's been around for a little while, so I know the sort of performance I expect from that. But I've run Geekbench on it, and that is my baseline of 1.0. And everything else in the column here for ratio is a ratio compared to that result. And it's the execution time. I also have a column for the coefficient of variance. Now, the coefficient of variance is the standard deviation divided by the mean. And this is a really interesting way of looking at variance. Rather than just using standard deviation, it gives me a percentage of variation within my results. And I'm looking for a lower number in the coefficients of variance. And if I see a lot of variance in there, I want to understand where that's coming from. Spend some time understanding whether, is it the test that's not performing well? Why am I seeing this? Is it the instances? Is it one instance that's impacted all of my tests? Or is it multiple instances that are always having variance? And you should spend some time understanding that. I also have a multi-CPU answer in here, and you can see in the multi-CPU answer that the CC2 8 extra large, it comes with 16 cores, and so it's actually telling me that I'm getting scaling on that platform for the integer test. I'm also seeing a lot more coefficient of variance, and that could tell me a couple of things. It could tell me that the systems are not very good when they run in multi-core. It might be I have, to be fair, the wrong AMI. Maybe there's some performance problems in there. It might be the test itself doesn't run very well in multi-core. And so it's worth spending some time, and I can tell you that, for example, Geekbench, the reason for this is because not all of the tests are multi-threaded. So you end up seeing a lot of variance because it's flipping from single-threaded to multi-threaded tests. And you can see the runtime here is almost consistently around 2 minutes. So this is a fixed time benchmark. Okay? So the more it can do in there, the result number is actually meaning faster rather than running shorter. When I talk about understanding run variance, when I said dig into the EC2s, what I'm doing afterwards is I'm actually taking a look within that run, one specific component, the M3 extra large, and drilling down to see what the one CPU ratio is, and making sure that it's all consistent and it's actually the same across all of the instances we tested on. You can also see the coefficients of variance in there is also very flat. When I break it out, because I want to see just the integer component, we see a little bit more interesting numbers. Now, Geekbench doesn't actually break down the timing for integer, so it's very difficult for me to use Geekbench to do that. So I'm not 100% sure whether Geekbench would be the right test at the end of the day for doing just integer in this part. But what you can see is that the coefficients of variance on the CPU integer part is very, very consistent. And so that's showing me that each of those instances is going to give a reliable result from there. So moving from Geekbench into UnixBench. UnixBench was developed for Byte magazine. It was a benchmark developed originally for some very old Sun hardware, and it gives you a relative score compared to that Sun hardware, so everything is faster than that today. And only just. And it's going to run 12 workloads. It takes about 30 minutes to run, and these workloads are broken down into integer, floating point, system calls, and file system calls. It takes a geomean of those results, and that produces an index score. So you actually get a score for your system. You're going to come out with a number that your system represents. It is open source, so you can take a look at what it's running. You can actually see how the code is written. Because of that, people have actually developed patches for UnixBench, sorry, because it doesn't run well over 16 CPUs. When they built this, the Spark architecture didn't even have 2 CPUs. So the fact that we now have 32 and more CPUs in boxes kind of throws it for a bit of a curve. The UnixBench script that we use to run this is very similar to the last one. We make sure that we annotate the outputs so we know where they're coming from, what time, and how long they took to run. The number of copies I want to run. So the number of copies I want to run is a simple grep of the proc CPU info to count the number of processors in the system. And then I'm going to run it. It doesn't have a very complex run line. It's simply run and then -c for the number of copies. Now, there's 2 -c's in here, and what this means is I'm going to run this benchmark in 2 modes. I'm going to run it single CPU first, and then multi-CPU second. And then we do probably could be done more elegant, awk and grep instead to put that into CSV, so we can put it into Excel, the world's heavily used analytics tool that we get for doing all of our results. All of these little charts come from Excel. So again, we did the same test we did last time where we took the CC2 8 extra large and used that as the baseline. And then we worked out what our CPU ratios were to the other ones. Now, you can see in here that the C3 is a little bit faster. The M3 is also a little bit faster on the one CPU. And the M2 is a little bit slower. Now, I understand that's because there are different generations of EC2 instances. And the C3, that's a compute optimized. M3 is our latest general purpose. The M2 is an older memory optimized. And because of that, with the different clock speeds they have, they end up giving us different results. And again, I can see my CPU ratios, but they're not scaling the same for this test. On the previous test, we were seeing a scaling of 16. And in this one, we're only seeing a scaling of 4 on the CC2, and the other ones, they're not even going up that much at all. And the coefficient of variance is also all over the place compared to the previous tests we ran. So either Geekbench wasn't giving us good numbers, or maybe UnixBench isn't giving us good numbers, but we definitely want to spend a moment and work out, well, what happened? Why is it different? And you notice the runtime, oh, we skipped over, the runtime is all consistent on that. So the runtime is the same. So this is, again, a fixed amount of time that this test is running. It's the work that's important. If I actually take the test to pieces, and you can do this, you can actually run individual components from it. And I run just the integer part, which is the Dhrystone 2 benchmark. I actually start to see the scaling I was looking for. I see that when we run on the CC2 8L extra large integer only, we're seeing 16 or 15.54 scaling on that. I also see my coefficient of variance is significantly lower. It's basically about just under 0 at that point. And I also see that my runtime is really, really short, 17 or 0.17 of a minute, so about 10 seconds it's running. Now, the Dhrystone 2 benchmark, I know if I run it independently, it can run for easily 30 minutes, no problem at all if I set it up to really stress the system. So I already know in here they've modified the benchmark to run very, very quickly on purpose. But if I dig further into the benchmark, I also discover that when you're running UnixBench, even in multi-CPU mode, so when I asked it to run 16 copies, it only did it for the tests that support multiple CPUs. So it still ran in the background a single-threaded file test and a single-threaded system call test. And so those numbers skew the actual performance of the system because they're basically taking away from the multi-threaded performance. Because if you were doing that truly multi-threaded, all of the threads would be doing system calls. All the threads would be doing file calls. Another CPU benchmark we spend a lot of time looking at, and internally we use quite heavily as well, is the SPEC CPU benchmark. Now, the SPEC CPU benchmark is what's called a competitive benchmark. That means that companies are actually required to publish all of the results, how they achieved the results, and then the configurations they used. It's heavily, heavily tested. It's commercial. You buy a site license to be able to run it inside your environment. It's been audited by many, many parties to ensure that it is consistent and the numbers that are used from it are very effective. And it comes in source code, so you can look at it, meaning you can also optimize it. And it's perfectly acceptable to take the spec benchmark and modify it to be appropriate for the architecture you're testing on. So for example, the latest Intel systems support AVX. You can ensure that you are using AVX when you compile the benchmark for this. It's very, very customizable. There's an awful lot of benchmark components in it. It takes about 5 hours to run the full benchmark, and you can go take a look at the results which are published on the SPEC benchmark website. And because they're published, it means you can also go and take a look to see how you're comparing your results to another comparable system. You can go look up a system with 16 cores and 60 gig and see how it performed, or the specific Intel version of CPU. There's an awful lot of benchmarks in here. I'm just pulling out a little subsection here. These are the ones which are going to be focused in around integer performance and of most interest to us. And the one specifically that we ran for this test was 429 MCF. So quick look at the script. I think it's pretty repetitive now. We get the idea that we annotate first and then run. I'm only running one iteration of this, and I'm not running the full 5-hour test. I'm just looking for basically a quick answer from the spec system. This one is going to tell me how long it took to execute. So this is a fixed work benchmark, and so quicker is going to be better. Again, we use the CC2 as the baseline performance. And you can see in here that we're seeing the similar scaling we saw with the Geekbench numbers when it first went up, so 16, and the same with the integer numbers inside UnixBench. So this test is confirming for us that the other tests are also giving representative data. You can also see the coefficient of variance in these tests is also quite low. And the runtime on these tests is much longer than our previous runtime. So this is not something you can just quickly run and get an easy answer like the Geekbench or UnixBench. You're going to have to be pretty committed to running this to get some numbers out of it. The last CPU benchmark I want to talk about is going to be Sysbench. Originally designed as a quick system test for MySQL servers, so it does a whole bunch of different things in there. It does a lot of different tests, file I/O, CPU memory, and you can choose whether you want to run each individual one. It's actually being used, I think, right now in another talk, the TCO talk, to compare CPU performance of different instance types. The source code is there, so you can build it. You have to build it. It also means you can see how it's running. It is really, really simple. The defaults will run in seconds. It will not give you any useful numbers. It will be so quick that a context switch will make a difference. So you really want to make sure you understand how you're going to run it. Taking a look at the Sysbench script that we're using. Again, annotator output. When we run Sysbench, we can feed the parameters we want to run. So in this case, I'm only going to do the CPU tests, and I'm going to be looking for prime numbers, integer-based, and I'm going to set that to 100,000 prime numbers, and that's actually going to cause the test to run for a reasonable amount of time. Now, because it's a time-based test, the quicker it runs, the more it's doing. If we take a look at this, our baseline again, we're going to use the CC2. Our coefficient of variance is actually pretty low, except on the C32 extra large. We're seeing an awful lot in there. And the runtime is really, really short. This is the default numbers if I run this with no extra parameters for the CPU test. If I tune it, and those are the numbers we set where we actually require 100,000 prime numbers, we can see now that the scaling is much more in line with what we expect. The number of cores is increasing. The CPU ratio is increasing as the number of cores increase. Our coefficient of variance is a lot better. It's not perfect on all of them. And our runtime is significantly longer, so we know it's actually doing something now. So if you're using Sysbench or you're looking at Sysbench, you definitely want to spend time making sure you're running the whole benchmark. So a quick comparison across all of those tests. This is really a little bit too much data to be pulling up on a big slide, to be honest. But we can see in here that UnixBench and the UnixBench integer give very different numbers. So if it's integer performance that we're looking for in UnixBench, we want to make sure we call out that specific component and not just rely upon the overall number to give us an indication. If we're looking at the Sysbench default tests, again, you can see the numbers are very different compared to tuned. So make sure you're actually calling out the tuned results when you do that. So moving from CPU into memory. Another hypothetical scenario, and I'm probably going to have to speed up a bit for our second talk here, but the memory-based testing, you could use some of the previous benchmarks, Geekbench, etc., but the one we're going to call out specifically would be Stream Benchmark. And in this scenario, we've already determined that we have a lot of memory requirements. We want to be able to drive 20,000 megabytes a second of memory bandwidth. And what instance would work best? Like, how could we choose an instance that's going to be appropriate for this? Again, we ran all of these tests on 1304, 10 times, 9 times. You get the idea. We're very repetitive in this. So the Stream benchmark is a very commonly used benchmark which provides 4 tests. It does a copy, scale, sum, and triad. A triad is the combination of the copy, scale, and sum. For our testing, we're probably only interested in triad unless we know specifically we're doing other operations. The results are published, although they're not very up-to-date. Not many people are publishing now anymore, but they are published if you're interested. The other thing that's actually very interesting is people like Intel will actually publish their stream results when they're launching new CPUs. So you can see whether you're getting what Intel expects you to get from your platform when you're testing. It needs to be built by default runs on 1 thread per CPU. So the more CPUs you have, the more it will test the memory bandwidth. I personally, and us internally, we use a tool called Stream Scaling, which is an open source project that will work out the right size of array to work on for memory testing. The array size within Stream has is very relative to the performance of Stream. So when it was originally developed, the benchmark operated on a couple of megabytes. Since then, we now have L3 caches that run up to 30 megabytes. So if you're doing a 2 megabyte Stream benchmark test, you're basically testing the cache. You're not actually testing the DIMMs that are in the box. So you need to make sure the array actually fits significantly into the box. So you want to be using something with a couple of gigabyte size of array. And there's some ways to work that out appropriately, but Stream Scaling deals with that for us. So the scripts are very repetitive. We do the same. You run it. You don't actually need to do anything. You just specify stream, and it will start up, and then we output these and publish them. And then when we run it with Sysbench, which is the one that runs the same benchmark, we can do some comparison. So if I take a look at Stream Triad benchmark and then the output from Geekbench, you'll notice that the numbers are not the same. And if I take a look at the default numbers, they're wildly off. And so the numbers from Stream Triad, from stream scaling, are what I expect. 55 gigabytes a second for a CC2 Sandy Bridge is close to what I expect. The Sysbench default looks awful. Now, the reason for that is the Sysbench defaults are very, very small. Again, it's just running inside cache, and it's not even exercising any of the cache. So you're not going to get numbers that are effective for that. And so definitely look at stream scaling. If I dig through the numbers, my goal was to find something that did 20,000 megabytes a second, so 20 gig. Almost everything except the C3 large would be able to service that request. If I was using the numbers on Geekbench Triad, I would have found myself only looking at one instance. So it's important to make sure you're getting the numbers you're looking for. Testing disk I/O. Now, I'm going to be giving a talk, shameless plug, tomorrow, a 45-minute long talk just on EBS. I could spend now another 2 hours talking about EBS and the different storage options. There's a lot to it. Testing them is also quite complex. You need to understand what you're testing. But I'll try and give you a little bit here to sort of get you started with how you might do that. So there's a lot of different configurations to it and a whole bunch of parameters the tests are going to do. So when you're choosing storage benchmarks, try and really understand what is the workload. It's very easy to use if we go through here. So, OK, I'll come back. So benchmarking provisioned IOPS in GP2. If you're going to be benchmarking that, if you're going to be spending time doing that, please, you must use an Amazon EBS optimized instance. If you're not using an EBS optimized instance, you're basically not caring about the consistency of the performance because your network bandwidth is going to be shared with your application. So that might be web requests coming in or people doing database requests. You're sharing the bandwidth, and so if you don't get the performance you expect, it's because the network isn't the way it should be designed. Create provisioned IOPS volume, attach the volume to the instance, pre-warm the volumes. Pre-warming the volumes is getting rid of that first access penalty so you can drive a lot more performance through it for benchmarking. Not something you need to do typically in production. And then you need to understand the queue length and the latency. Now, network attached storage means there's a pipe between the instance and the volume, the EBS server. The queue depth, the queue length, is the number of IOs that are in there. The more IOs you have in there, the more you can drive the volume, but it also increases your latency. And so what I'm calling out here is the fact that as you increase the queue depth, you will impact your latency. So you need to find the right queue depth, and it typically means the number of threads running on your system or the amount of work it's doing. Testing disk I/O, there's a lot of different ways to do it. I see a lot of people still doing DD and copy. If you're doing DD and copy, you're actually testing page cache. You might as well be testing the L3 memory in the box again. It's not actually testing the disk. It's just checking how fast Linux or Windows can copy something. The one we use internally, the one we spend a lot of time on, we're working very hard to publish how to do an FIO benchmark, is the FIO, Flexible I/O Tester. The configurations for it can be a little daunting. You can take these away and dig through them, but it enables you to do a lot of very controlled parameters, including things like direct I/O or the size of file you're testing on, how long you should do the test. You can do fixed work, you could do relative work, you can do a whole bunch of stuff in it. I advise you all, if you're not using FIO today for disk testing, spend some time and use it. Just to pull out some of the differences when we're doing the testing and why you should be looking at real testing for this. The differences here in time is I do a copy first, and you'll see that it says it took 59 megabytes a second. If I do an RM on that, it says it did it at 1.2 gigabytes. These numbers are not real, and that's why FIO truly gives numbers you can rely upon as we go through that. If you're moving away from just doing simple I/O testing, please make sure you're leveraging things like the CloudWatch metrics that publish it, or understanding exactly how many, or pulling also together the larger configurations, things like striping, etc. So to summarize on the benchmarking, if you have to do synthetic benchmarking, please make sure you're testing something that's practical for your application. You can only use synthetic benchmarks if you're careful. Choose the best benchmark that represents your application. Know what you're going to be testing for. Analysis, make sure you know what best means. Make sure you know why you're testing it. Run enough tests to understand variability. A baseline, make sure you know what a good result really is. And samples, keep all of your results. Please push all of your results to S3 or Dynamo or MySQL or something of that nature. And with that, I'd like to introduce Benny Johnson from Just Eat. Benny's going to talk us through how they're actually doing application and benchmarking in their environment. Thank you, Benny.
Thanks for that. So as Dougal's left me 15 minutes, I'll have to rush. So as Dougal said, I'm Benny Johnston. I'm the head of APIs at Just Eat. I've got a quick one slide on what Just Eat is, for those of you who don't know, and then I'll get into how we automated our application benchmarking. So Just Eat, we're an e-commerce takeaway site. We don't cook takeaway, we don't deliver takeaway. We provide the technology that consumers can order that takeaway from a multitude of restaurants, and those restaurants can update consumers on the progress of the orders. About 2.5 years ago, we decided to move out of our data center into AWS. It's about a 12-month-long process. And after 12 months, we'd successfully moved everything from dev to QA to integration to production, all into AWS. What AWS services do we use? Basically, if AWS release it, someone in Just Eat will find a use for it. I'm quite sure right now, someone's in the office trying to work out how to use code deploy. So that's Just Eat. Before I get into how, I just want to say sort of why we were doing automated benchmarking. So we're moving out of the data center, okay, we're moving into AWS. We need to find out what sort of instance types to run on. There was a lot of sort of manual benchmarking and finding the best instances and stuff like that. And that was all fine, you know, to put it into spreadsheets and wondering what you did when and stuff like this. But it became apparent that we really wanted to automate it for, I'm going to use the public API as an example of this talk. And our public API is basically orchestration and authentication layer around our internal APIs that provides the data out to our apps for iPhone and Android, that sort of thing. And at the time, we weren't able to pilot them, so it was very important that when we released application updates to the public API, we weren't going to negatively affect the consumers. And that's, you know, if we changed the AMI, or if we changed the SDK, or if we made significant application changes, we wanted to make sure we weren't going to have a negative impact. So it was worth spending the time to automate our benchmarking. So what do we need when we're benchmarking? We need a known state environment. We need a set of tests, and we need some metrics. So how do we get our known state environment? Well, at Just Eat, everything's using CloudFormation. We've got our own little bit of custom tooling around the top of it. We looked around. What are we doing? What's out there at the moment that we're using? Oh, we're using TeamCity. That does our builds and our deploys. Let's use it to deploy our environments as well. So we're hooked into TeamCity, and from a single click, you can launch an entire environment that you would need in your own VPC to run the public API. So all the internal APIs it needs, the Dynamo tables, the throughputs, all those sort of things are launched for you in a known state. And we launch what we call sort of development-sized stacks. So it's the same EC2 instance type that we have in production, but only one of each instance. We don't run 24 of these. That's not what we're interested in when we're benchmarking. And we run these all in the same zone because we don't want to have latency on some benchmarking tests that we don't have in others. So that's our environment. Cool. What else do we need? We need a set of tests. Again, looked around the company, found this tool WAPT that the website guys were using for their performance testing. I'm sure you've all got your own favorite performance testing tool, but you know, so we went through, okay, we need to create a set of tests to test this public API. Who are our users? Well, the Android app, the iPhone app. What do they do? Okay, they do 3 searches, and then they look at 7 menus, and they build 1 basket, and they add 10 items to this basket. And you get an idea of, you know, the users of your application, the use cases of your API. And we build those scenarios into this, and you know, little loops and if statements to try to get those averages right. And really, you're making a best guess, and you don't really want to be guessing. So we have a look at the metrics out the other side, and a little later on, I'll tell you where we get these graphs from and how. But for now, what's important, the one on the left here is production at one of our public API instances in production on a Saturday night. And the one on the right is the same, you know, public API instance, but during our benchmark testing. So you can see they're not perfect, they're not identical. But I'm trying to coin a phrase here, this comparable load ratios, and it's a terrible phrase, and if you can think of a better one, tell me at the Q&A. But what we're trying to do here is, you know, for every 6 calls to get basket, there's 2 calls to add item or 2 calls to update item. It's trying to make sure that we're stressing the API in the right way that we would be in production. There's no point putting in, you know, the same number of overall calls per second if all those are just going to a local cache, whereas in production, it's calling other APIs and going off to Dynamo. We want to make sure in our performance testing environment, we're recreating that same comparable load ratios. So now we've got an environment, we've got our set of tests. What we're looking for now is automating this. You know, I want this to run every day. You know, I'd love to hook it up to our continuous deployment, but I don't really, you know, we run it for about an hour, and so we run it nightly. And our scheduler here is TeamCity. It will launch our environment in its own VPC, all the instances I talked about. Then it'll run the test runner and all the test agents, again, all through CloudFormation, they'll all launch. They fire off, run for an hour, run all those tests that we set up, get the results back, store them in S3. So what are these results? These are what API methods were called, how many times they were called, and how long they responded. Well, that's useful. I mean, hopefully those figures haven't changed, but realistically for benchmarking, you need a lot more metrics than that. Our CPU could be, under twice as much strain for this new application release, and as long as it didn't go over a tipping point, it wouldn't have affected those response times, so you won't know about it. So this is where our next step comes in down the bottom here, our results publisher. And at this stage, we can tear down those features under test. We can get rid of those test agents, those test runners. We don't need those anymore. We've utilized them for the hour, get rid of them. And then we go to our monitoring server. So we don't tear this one down because we want to go off and get the metrics off it. So I'm just going to sort of dive into what our monitoring server is and how we get metrics at Just Eat. So when we first started moving into AWS, it became apparent that CloudWatch wasn't up to spec for what we needed. The retention period, the granularity just wasn't what we needed for our production system. So I went around looking on the open source market, found StatsD. It sits there and basically it aggregates your stats for you. It sits over a Carbon backend, puts in little 10-second increments and does some basic statistical analysis on them. And then Graphite produces nice little graphs that you saw earlier, so we can get little pretty lines about whatever metrics we're collecting. So this is what we use to collect and display metrics. Now, what sort of metrics do we want? So there's sort of three types of metrics as I see it, and that's our application metrics. So yeah, all those initial ones we've talked about already, that what was called and how many times, how long it took, but also what that API then did. How many calls has it made to Dynamo? How many calls has it made to SQL? How long did those take? I want to hear about all those because I want to know if my next version of my application is using twice as many Dynamo calls. I want to know that before I release. Sure, I could just release it, and when the alarms go off, increase the threshold, but I'd rather not do it that way. I'd rather know before I release that it's going to be using twice as much of another resource. So that's our application metrics. Then you've got our hardware metrics. So we're a .NET shop at Just Eat, so we're all running on Windows. Our hardware, don't boo. So our hardware metrics we're interested in CPU, memory, disk queue lengths, garbage collection, context switching, all these sort of things. In Windows, these are all stored in Performance Monitor. So again, went looking on the market, found this tool called PerfTap. It basically just runs every 5 minutes, consults its config, what metrics are you interested in, ships those off to StatsD. Now we wanted these same metrics on all of our instances, so this is baked into the AMIs that are used in Just Eat. You'll get this by default. So that's our application metrics, our hardware metrics, but there's also AWS metrics that you just can't find anywhere else. And for us, it's really our DynamoDB throughput and our SQS queue lengths. We looked around, couldn't find a tool, had to actually write one ourselves this time. So it's just a little Ruby cron job that runs on a small Linux box in each sort of VPC. And we'll ship every 5 minutes, it'll ship these AWS metrics into our StatsD. So now we've got the three different types of metrics we're interested in. We've had our environment, we've run our tests. Now let's start to put those together and see what we can see. So again, we're using TeamCity. This somehow has turned into a TeamCity talk. But basically, our results publisher is then going to go off and look at all the metrics. And how does it know what metrics to go off and look at? So in GitHub, we've got our source. We've got all our tests. We store those in GitHub with our source. So for this version of the source, these are the benchmark tests I was running. And we also have a little comma-separated file that's just, here's all the metrics that I'm interested in for these tests for this version of the code. And you can go back at any point in time. You should, in theory, be able to recreate that. And if you're storing your CloudFormation there as well, you'll get all the same instance type that you had at that particular time. So then our results publisher will go off, produce these lovely little graphs, do some basic statistical analysis, find your 90th, 95th, 99th percentile. After seeing Dougal's talk, I'll now add coefficient of variance to this. And I'll go off, and we can put some hard figures in that list of metrics. These are all the metrics I'm interested in. It shouldn't go above this value. It shouldn't go below this value, that sort of thing. But that gets really fiddly, and I don't want to be sort of changing that all the time. So what we're more interested in is what's changed since the last time I ran this. I've just changed the SDK we're using. This ran happily yesterday. It's ran today. What's the difference? And this is where we make use of another TeamCity feature, the statistics page. And this is typically, I believe it was supposed to be used for showing your build time or your compile time. But it's just in your build log, you just output little commands and you can get the statistics graphs for you. So what we're seeing across the bottom here is a month of benchmark testing nightly on our public API. There's gaps in this graph because we don't benchmark on the weekends and because we don't release on the weekends. We're not making change. And circled in red here, you can see one of our methods actually decreased. It got slower. And this broke the build. So you can break the build and say, you're not allowed to deploy the public API anymore until you fix these metrics and get these values back down to where they should be. And from the looks of it, 4 days later, someone did do that and fixed it, and we're able to move on. So that's how we've done automated benchmarking at Just Eat. I've got a few minutes left, so I'm going to tell you about stress testing and how we've sort of made use of that same infrastructure and those same ideals to do stress testing. So basically, stress testing, we're not doing this automated. This is a manual thing we're doing. And what we're doing here, instead of me just launching all the stacks I need for the public API, I'll get the website guys ones as well, launch all their stacks, the call center, launch all their stacks, and not the development-sized ones, the proper production-sized stacks. So, in my VPC, I now have an entire replica of our production-sized system. And I'll use, the same tests that I have, but plus the website guys ones, plus the call center guys ones, and should be able to put our production load. So I start putting 1,000 orders a minute into the system, and it should handle it fine, because that's what it was doing on production on Saturday night. And then we start to scale this. We go, okay, what does it look like if I put 1,500 orders a minute? What components do I need to scale? And it's useful in this, there's components in our system that aren't necessarily horizontally scalable, and you want to know how much headroom you've got there. Our NAT's not horizontally scalable. How many orders a minute is it going to take before this becomes a problem? Okay, we've got about a year's worth of growth there. That's fine. I'm sure AWS will release it as a service before then. So the other thing, you're doing here, you want to find those bottlenecks, but you also sort of look at the pieces you're scaling and try to understand why you're scaling them. And so I've just got a quick war story on an architectural change we made through stress testing that we didn't expect to come up, but it's just something we found. So our business logic isn't terribly important here or exciting, but we've got an order engine. It's putting order state change messages. There's a SNS topic, order state change, and the order engine's firing down, this order, it's been paid for. This order, it's been sent to a restaurant. This order's now in a kitchen, going into that SNS topic. And then we've got little workers that want to process and listen to those messages and respond and do certain work on them. So they're on queues, hooked up to SNS. It looks fairly typical. It looks like, hopefully what it should. And then, we start scaling twice as many orders. So twice as many order engines. Yep, that makes sense. Twice as many order resenders. Right? Wait, it's only a small percentage of orders that need to be resent. Why are we now running 6 M3 medium order resenders? It just didn't seem right. And when you look into it, you can see what were those order resenders doing? They were spending most of their time reading messages they didn't care about, they weren't responding to. So we changed the architecture, so we had a topic per order state. So there's a order unacknowledged state or an order in the kitchen, order in the kitchen topic, and each of those queues off each one of those topics. And this meant order resender was only ever receiving messages that it needed to resend. So, I'm sure there's an AWS white paper that explains exactly this that we just didn't read. But, it's just one of those things that we found through stress testing that, in the end, saved us money, which is always a good thing. So, that's Just Eat. That's how we automated benchmarking. That's how we've used stress testing. Hopefully that was useful, hopefully interesting. I'll be available for Q&A afterwards.